Greetings, Earthlings. Today I want to go over polygons and how to find angles. Now, I might normally do this a little bit later in the geometry series, but I thought it would be much more valuable to keep going through this theme of hammer time, using our hammer. So that's why I kind of moved this up front. Alright, so what sort of questions are we trying to answer? So let's say we have something like a hexagon. Now, for our purposes, I'm just going to focus on the hexagon, but you can do this with any other shape. You can do this with pentagons, octagons, nonagons, heptagons, whatever. So let's assume this is regular. So regular is a technical word. The word regular means all the sides and all the angles are the same. So in layman's terms, it just means it's a nice symmetric looking shape. So it's not an oddball polygon. Okay, so throughout this video, let me back up a second and tell you guys what is the outline of this video. So we're going to be using our hammer, and I'll discuss what that is. And we're going to basically go over 3 ways to find either the sum of these angles or an individual angle in the case of a regular polygon. And those techniques are going to be in, on, and out. Those are the cue words. I'll explain what those mean. So in general, let's say this is not a normal hexagon, so let's say it's kind of like this or something weird. Then clearly, let's say if we focus on these 2 angles, this angle is larger than that angle. So if the polygon is not regular, we may not be able to find every single individual angle. So for our purposes, I'm going to assume we either want an individual angle where it's a regular polygon and they're all the same, or we want to find the sum, which is always going to be the same no matter the shape. And we'll see why that's the case. So I'm going to focus mainly on this regular case, but like I said, just know you could apply this for the sum to other cases. Alright, so first let's discuss our hammer. Now, polygons can be intimidating because they are many-sided. They're not triangles, they're not squares. So we have to think, what do we already know that we could use to find the sum of all of these angles? Well, what's simpler than a polygon? We started off with lines and triangles. So that's it. Those are going to be our hammers. We have 2 hammers. Now, we know that a line has 180 degrees and a triangle has 180 degrees. Now, the line doesn't immediately jump out to us, but just know that all 3 of these techniques are basically going to boil down to using either lines or triangles, mostly triangles. Alright, so when I say in, let's go, so this will be technique number 1. Technique number 1 will be pick a point inside the hexagon. I like to pick the very center, but for proving the sum of the angles, it doesn't have to be the center, it could just be the interior, anywhere on the interior. Let's say it's the very center, but it could be over here, anywhere. Alright, so in really stands for inside or interior. Now, here's what we're going to do. We are going to chop this up into triangles, because that's our hammer. Let me remind you guys, the question we're trying to answer is what is the sum of all these angles, and or what is one of these individual angles in the hexagon. So we've chopped this up into 6 triangles. We know that one triangle has 180 degrees. And by the way, within the interior, the inside method, or chopping from the center. You can think of these as chopping instead of in and on. I just thought it would be easier to remember it that way. So whatever floats your boat. So this is going to kind of have 2 parts within it. So let's do it kind of one way first. So think of this as 1A and 1B. So 1A, we are going to do it this way. This is a circle inside here. So that's 360 degrees. And since there are 6 of them, 360 divided by 6 would be 60 degrees. So that's where I got that 60 degrees, because 6 of the same thing must get you a full circle. So once we figure this out, then we think about, oh, this is a regular hexagon, meaning everything is symmetric, so all of these triangles have to be the same. So that means if we take this triangle and go like this side has to become this side, so these sides are the same. And that goes all the way across. So the tick marks just indicate they're all the same. Now that means this is an isosceles triangle, and if these two sides are the same, then these two angles must be the same. And what does that mean? They sum to 180, that's 60, so these two must make up the 120. And therefore they're both the same, so they must be 60 each. And since we care, let's say about, let me do it a different color, we care about this entire one, then that would just be 260, so that would be 120 degrees. That would be our interior angle for the polygon. Now, so that was 1A. We basically chopped it from the very center and worked our way out through the triangle. Now here's another little tip. We didn't even have to find the 60 because we know that two of these sum to 120, and this angle is two of these angles, same thing, so we could have just stopped at 120 because what we did, we got 120, we divided by 2, and then we multiplied back by 2, so we didn't need to do that. Alright, so that's method 1A. You take any shape, so you can take a pentagon, do the same thing. You chop it from the center. There are 5 of these, 360 divided by 5 will get you 72. These two have to add up to, these are the same thing, so 180 minus 72 means together these are 108, and there's 2 of them here, so that means this angle is 108. And that is a nice way of finding these angles. So you can pick any polygon you want. Alright, so that's method 1A. Let's do method 1B. So for method 1B, we're going to use the same sort of idea, but now we're going to try to find the sum of the angles. Now, what I'm going to do is, I'm just going to go through the method, and I'll also comment on, because this is the part you might not come across very often, which is, well, which method do I use? Which method is better for what? So as we go through these, pay attention not just to what is the method, but when do you, when might I want to use this method over that method? One of my favorite methods is 1A, the in A, because this allows you to find other things later on in the series like areas and volumes of shape, because you're working like in the nitty-gritty stuff, whereas a lot of these methods, they might be better for some things, but like for example, they might help you find the angles, but that's about all they're used for. So this is, when this works, this can be much more powerful. So that's kind of my take on it. Let's go to 1B. So again, we're going to have our hexagon. We're going to chop it up. Now, let's think about this. We have 1, 2, 3, 4, 5, 6 triangles. So that's 6 times 180 degrees. So if we were to add up all of these angles, we would have 1,080 degrees. Except, if we want to find the sum of the angles of a hexagon, we don't care about this inside stuff, so we want to subtract that out. That's 360 degrees. We don't want 360, we want to deal with 180s. So what is 360 in terms of 180? Well, it's 2 180s. So we could subtract off the 2 180s, which represents this center, and then we're left with 4 180s. So if you were to multiply this out, you would get 720 degrees. Now, the famous formula that you might have just memorized in school, or you might have seen, is this n minus 2 times 180. So this is something you should definitely know, and what we've just shown is how to get that in a special case. But in general, let's say you have not 6 sides, but n sides, you would have n triangles. You subtract off 360, which is 2 180s, so that would be n 180s minus 2 180s. There you go, we just proved the formula. So that's just an example for the hexagon case. Now, from here you could also, this is like, now we're doing 1B. 1B meaning we are thinking about finding the sum first. From here you could divide this by 6 to get what is each individual angle. So if you take that formula divided by n, you will get the angle measure per each angle. That's fine. I'd rather not find this large number and then divide. I'd rather find it directly if all you care about is the angle. Alright, so that's method 1B. So recap. For 1A, we found the angle first, whereas for 1B, we're trying to find the sum of the angles. But in either case, the technique involves chopping from the center. All right. Let's move on to number 2. All right. Now, this is a really nice technique as well, and I actually think it's much simpler for proving this formula, but it's not very versatile, which is why I put number 1 first. That's my favorite one. So let's draw our hexagon. Now, we were inside. On, we are on the thing. Now, technically, we're not on anywhere. We're going to be on a specific point. We're going to chop from a vertex. So any one of these will do. Or a corner. Vertex is corner. So pick your favorite corner, and we're going to use our hammer. So what's our hammer? Lines don't seem useful. Let's use triangles. So chop this into triangles. Now, in general, you should be able to convince yourself that if you have an n-sided shape, you should have n-2 triangles. So we have a 6-sided shape, and we have 4 triangles. That's 2 less than the 6. Why is that the case in general? Well, let's see. The first, so think of it as like, okay, each side kind of gets its own triangle, except these neighboring, so how can we think about this? Okay, so from this point, there are 6 points, right? 1, 2, 3, 4, 5, 6. This triangle will hit one of these sides. That's 1, 2, 3, 4. And the other 2 are neighboring sides, so those are already part of these triangles. So that's why it's 2 less. Does that make sense? So, like I said, just quick recap because that might have confused you guys. So for this triangle, if we're from the perspective of this point, the opposite side to this point is right here. So that's 1, 2, 3, 4. These 2 have already been counted as part of these 2 triangles because these are adjacent sides. And that's why we don't always have 2 fewer triangles than sides in the polygon. All right. So because we have 4 triangles, what are we trying to sum? We're trying to find the sum of all the angles. That means we want this plus that plus this plus this plus that plus that. Now notice, this actually might not be very obvious. If we sum all 4 triangles, which would be our 4 times 180, which you should remember is the right answer from the first technique, that does correspond to adding up all the green stuff. Why is that? Because this angle is that angle in the triangle. This green angle consists of this little guy and that little guy. This consists of this and that, and this one consists of this and this. That is itself, and this consists of all these little parts of the triangle. So, unlike the first technique where you had this center thing we had to subtract, which wasn't part of the sum of the angles, here this is faster because there's nothing in the middle. There's no extra stuff. Like adding your 4 triangles is your sum of the angles. So there you go. So we just proved that this is the formula for the sum of the angles in a polygon. Now you guys might be wondering, why don't I just memorize this formula and forget the rest of the video? You might forget this formula. Also, this doesn't really expand your knowledge. It's much more useful to think about many ways to get this formula. That's how you really get better at this stuff. So if you have an exam and that's all you need, then I get it. But if you're like, hey, I'm consistently confused, or I want to get to that next level, this will really give you that long-term fundamental stuff. All right. Now, let's go to technique number 3. And by the way, before we go to technique number 3, when you're using this, like let's say you just have an exam or something, it's a little bit of a quick tip, and you forgot, you're like, is it n-3? Is it n-2 times 180 times 90? What is it? A nice way, if you don't really have much time to figure this out, try for a triangle and a square. So let's say you thought it was n-3 times whatever. Well, let's say you thought it's n-3 times 180. you know that's supposed to work out to be 180. So if you plug in n is your number of sides, so that would be 3 minus 3 is 0. That's no good. So you try, let's try 2. You're like, oh, maybe was it 90? Maybe it's 2 and 90. So that 3 minus 2 is 1. 1 times 90 does not give you 180. So then you could quickly remember, let's make this 180. And so that would be 3 minus 2, 1 times 180 is 180. And then let's try that here. 4 sides. 4 minus 2 times 180 is 360. And indeed, we have 4 right angles. So you can quickly check it in those cases. That's a little bit of a tip if you just forgot it and need it remember really fast. All right. Now, technique number 3, which is very cool. Like I said, techniques 2 and 3, I don't use that much, but they are pretty cool. So let's see what that means. So in meant inside or interior. Out is going to be outside or exterior. I didn't want to write it in these big words because I think it's going to be harder to remember. Whereas if these little short words, you can basically be here, here, or here. That's it. All right, so let's do our favorite hexagon again. Now, here's the thing. We are going to consider an exterior angle. So we're going to take this angle. That's going to be our focus. So that's the out part. That's what I'm referring to. So what are we going to do? Let's take this. So let's say this is x. And we are going to do the same thing on each side. So think of it like a sun. We're going to extend each of these segments. All right, so we have angles here, 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 and here. Now, in the case of a regular polygon, all of these x's by symmetry, these will all be the same, right? So these are all x's. But it doesn't have to be a regular polygon. The logic will work just the same. So don't freak out if these are not all the same. However, if they are, you can find more stuff. So you'll see what we can find if they are all the same. So here's the idea. We want to find the x. In fact, this might be the fastest method to find, if you just want to find what is this interior angle of the polygon, I think method 3 is probably the fastest method. Method 1 is good too. So what I really recommend is take a problem, like find the sum of the angles in a decagon, find an individual angle, and try out all 3 methods and play around with the methods versus the type of question you're asked and figure out for yourselves which is the most efficient. So I have my thoughts and you can just listen to my thoughts, but you're going to learn it better if you just mess around a little bit. All right, here's our idea. We're going to pretend like we're an ant. So we're a little ant. So we're facing this way. Okay, so I'm going to draw, that's our ant. Okay, so we're facing this way. Now we are going to turn x degrees. Now we're going to walk this way. Now the walking we're going to ignore. So we're going to walk this way. Now we're going to turn again, x degrees. Walk, turn, walk, turn, walk, turn, walk, turn. And now we're back facing the same direction. Now you may have not realized what we've done, so what really helped me was drawing a smaller diagram. Let's shrink this so it's really, really, really tiny. In fact, it's so tiny it's almost like a point. I'll make it not quite a point, but you'll see what I mean. So let's say it's like, all right. So by making this almost into a point and ignoring the walking along the perimeter of our polygon, all I want you guys to focus on is just these turns, right? So what have we done? We've made 6 turns. Let's look at this. We've made 6 turns, and each turn was x degrees. Now, and we've come full circle, right? We went from here to back to the starting point. So a circle is 360 degrees. So if it took us 6 turns to get 360 degrees, divide that by 6, you find that x is 60 degrees. 60 degrees per turn. So maybe the and thing didn't help, but I found that kind of cute. Okay, so if we know that this is 60, then now we use our line. That's where I said that's only going to be used for number 3. So this whole line is 180, and if this is 60, this remainder portion must be 120 degrees. So I think that's one of the fastest way to find that. Now, you can actually use number 3 to do this as well, and let's see how you might do that. And by the way, that's something I never even thought about. I only realized that as I was preparing for this video for you guys. So I learned stuff as I present stuff to you guys. So I'm great. Thank you guys, whether you know it or not, for that. So let's prove not just how to find this angle, but how to find the sum of all the angles using the same technique. We're going to use our lines again. So each side is a line, right? So imagine this angle were opened up to be the full 180. So it is just this line. This is a full 180, that's a full 180. Everything's a full 180. So we'd have 6 180s, right? Because there are 6 lines if you extend each of these. Except we don't want to count this stuff, right? All these x's are not included. So it's going to be smaller by x per each line. And all the x's add up to 360 degrees, which if you remember from technique number 1, 360 is 2 180s. So instead of doing 6 180s, we have to subtract 2 180s. And 2 180s is our 360. So we're left with 4 180s. So this is the same way of getting what we got in number 1. So we found that the sum of the angles will be 720 degrees. So again, we're getting n, which is 6 in our case, minus 2 times 180. Now you could try this for pentagons. In fact, if you want to put like a little homework exercise, try this for pentagons, heptagons, decagons. Try this for various shapes. I would say if you want to do this at least 3 to 5 times to start to get the hang of this. So my advice, if you want to do this like really properly, for each of these 3, I want you to use each of these 4. So these 3 and 2 methods within number 1. All right. So that's all I have to share with you guys today. There's a challenge. This is really for like folks that really want to take it more advanced. So this is really all you need to know. So this is going to be way out there. There's something called a platonic solid. So if you're interested in the history of mathematics or like ancient Greek history and stuff like that, a platonic solid is a 3D shape made out of all 2D shapes of the same type. So for example, a cube. A cube consists of only squares. It's square, square, square. There are 6 squares. You could be a tetrahedron, like a pyramid. So I'm just going to draw a tetrahedron. Here's your tetrahedron. It consists of 1, 2, 3, 4 triangles. Now, so that's it. Those are examples of platonic solids. There are only 5 of them. There are tetrahedrons, cubes, octahedrons, dodecahedrons, and icosahedrons. Now you can look up what those prefixes mean, but you might want to ask yourself, why are there no other shapes? Why are there only these 5? Like, why couldn't I have a shape made out of decagons or something? So really think about this. I'll put a link in the description where you guys can read, some clues and ideas as to why that's the case. But think about that, and maybe like a hint might, well, I'm not going to give you a hint. Just think, why are there no other ways to get 3D shapes using exactly the same materials? All right, I will see you guys in the next video.